Hi, this will be a quick recording to walk you through Unit 6.2, which is on security, privacy, and integrity of the Cambridge Computer Science AS level syllabus. Uh, and with that said, let's get started. So the very first thing we'll look at as part of this lesson is about data integrity, specifically what data integrity means and how do we enforce data integrity in a communication for data at rest, that's data stored on a machine, and data on the move, that's data being transmitted between computers. So data integrity is defined as the means of ensuring that data is accurate, complete, and consistent during three stages: during input, storage, and transfer. That's data integrity. So it's about making sure that the data is correct, complete, and consistent. Data integrity can be achieved in two major ways, guys, using data validation and data verification. What these two things mean and what their differences are, we'll take a look at in the next slides. What's data validation? Data validation is about checking whether the data is sensible, reasonable, and allowed. You can imagine that data validation is about checking if the data is in the right format, for instance, right? Now, for instance, just to take an example, right? Let's say you're typing your date of birth when signing up to Facebook or Instagram, when you're making a new account. Maybe they expect you to enter your date of birth in a specific format. Maybe the format is DD/MM/YYYY. Now, when you type in your date of birth into these systems, you're expected to type it in this format. Now, if you type it in a different format, it fails validation. It means that you're entering the data in a format that is not the correct format or the format that is accepted by the system, right? Now, does this, however, ensure whether this is the user's true date of birth, though? Now, let's say Instagram or Facebook enforces that you type in your date of birth in this format. But is this a way of ensuring whether this is the user's actual date of birth? No. I mean, the user can enter any date of birth as long as it's in this format. Therefore, validation does not check correctness, right? It checks whether the data is in the right format, whether it's sensible, reasonable, allowed, but not whether it's correct. That's for data verification, right? So you can imagine that data validation is about checking whether the data is in the correct format, but not whether the data is correct in itself. And data validation is used during data entry to prevent invalid data from being accepted. Okay, so it's about preventing invalid data during data entry. Hopefully that makes sense, guys. We'll take a look at the types of data validation that you guys have in your syllabus. Keep in mind, you might have to list out types of data validation and also give examples of the different types of data validation, right? So make sure that you guys pay attention here. First, the first type of data validation is a range check, which ensures that a number or date falls within a set range. For example, the age must be between 0 and 120. That's a range check to check whether a number falls within a set range. Format check ensures that the data follows a specific pattern or structure. For example, you could take the date of birth situation where you're supposed to enter the date of birth in DDMMYYYY format. Another example could be that the phone number must be in the format of +94 or whatever your country code is, followed by 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. No, if it's anything but this format, the data is not accepted. So we talked about range check, format check, and then we have length check. Length check is to ensure that the data has the correct number of characters. For example, the postal code must be 5 digits long. Anything less, anything more, not accepted. Then, in addition, we have presence check. Ensures that required fields are not left blank. For example, when you type in a name into a system, that name must be typed in. You cannot leave it empty. Now, this is very commonplace in maybe quizzes that you guys have taken on Google Forms, for instance, where they tell you that that entry is required with a nice star mark. You might have seen a star mark next to some entries, which means that you cannot leave that you cannot leave that entry empty, right? You cannot leave that field empty. In other words, it's required. That's an example of a presence check to ensure that required fields are not left blank. Existence check ensures the data exists in a predefined list or database. For example, the product ID must match one already in the database or already in the inventory. Now, a very good example of this is when you guys get drop-down lists, when you fill forms. An example could be when you have to, let's say, select which country you are from. In a site, when you're trying to register to a website, they ask you to select which region or country you are from. Usually, though, they don't let you type your country, they expect you to select it from a list. That's an example of an existence check where you ensure that the data exists in a predefined list, which ensures that the user won't misspell countries or select countries that don't exist, because we know there's only a finite list of countries. So it makes sense that the user selects one of them and not anything else. Limit check is a similar check to a range check, but only checks one of the boundaries, right? So a range check checks within a range, lower and upper bound. Limit checks whether it's below an upper or above a lower. It doesn't check both. So a limit check ensures that the quantity must be not more than 100, for example, because it only checks whether it's not more than 100, not whether it's not less than something or whatnot. It is only a single check, only one boundary. That's all. So we have presence check, existence check, and limit check. And previously we discussed about range check, format check, and length check. So take 6 types of data validation methods, all of which you should try your best to keep in mind. Then finally, we have a very interesting type of data validation called the check digit, which is a mathematical check that is a check that uses an extra digit calculated from the other digits of the data. It's a mathematical check using an extra digit calculated from the other digits of the data. Now, I'll explain this to you with an example, but the idea here is that you transmit the data that you're sending with the check digit, and the system on the other hand side can recalculate the check digit and compare it to the original. But keep in mind, check digits are also data validation because you don't ensure whether the data is correct. You only ensure that the data is in the right format or is in the right structure per se, because the different kinds of data may yield the same check digit, right? Different kinds of data may give you the same check digit. You see check digits being used in barcodes and ISBN numbers, right? To not ensure whether the barcode or ISBN number is correct, but whether the barcode or ISBN number is in the correct format, or whether it's a legitimate barcode or ISBN number. That's a check digit. It ensures that on transmission, the data itself remains untampered, and thereby the system on the other hand side can calculate the check digit and compare it to the original. Then let's take a look at an example of a check digit with a simple algorithm, guys. First up, we have to take a look at an example of data like 4372. Let's imagine you're transmitting 4372 over the web, or you're saving it in your machine, and you want to make sure that this data is in the right format, it's consistent. So you want to make sure that 4372 is 4372. What can you do to ensure this? You can first calculate the sum of these numbers. You can add these numbers, for example. Step 1, add those numbers, right? Add the numbers. So let's add the individual digits in our number. 4372. What will that give us? That will be 7 plus 7 is 14. 14 plus 2 is 16. So you can imagine the first step of a check digit calculation could be, for example, adding all the numbers. Now, this is in no way saying that this is the only way to calculate check digits, guys. There are lots of algorithms like ISBN 13, which is an algorithm for calculating whether ISBN numbers that are 13 digits long are valid. Technically, ISBN is a 12-digit number, but the 13th digit is a check digit, right? So the ISBN 13 algorithm is there to generate or ensure that the 13th digit corresponds to a valid ISBN. So you add the numbers 4 plus 3 plus 7 plus 2, and you end up getting a sum. And then what you do is you pass that sum into some kind of check digit equation. So you pass 16 into an equation like this. You in no way have to remember this equation for the exam, guys. Forget about it. You don't have to worry about this. This is an example. So you pass this 16 into a check digit equation. Pass into check digit equation, right? You pass it into a check digit equation, and let's calculate what we end up getting. So this will be 16 mod 10, which is 16 divided by 10 and its remainder, that will be 6. 10 minus 6 would give you 4. Then 4 mod 10 will give you 4, right? Because 4 divided by 10, remainder is 4. And then what do you do? Before you send or save your data, you attach that 4 to the end of the original data. So this becomes your so-called check digit. Now, is this 4 part of the original data? No, it's not. It's just there to ensure that this data is correct. In other words, whether it's in the right format. 4372 is given the check digit 4 based on this algorithm. On the receiving end, what happens? On the recipient end, when it receives 4372 with an additional check digit of 4, or when you want to double check your data that may be already saved in your database, or maybe saved already in your computer, you could take this data with the 4, with the check digit, and what you could do is you could recalculate the check digit using the original expression for this data. Then, hopefully if you use the same data and if the data hasn't been tampered with, you'll end up getting a 4. And if you compare the 4 that you recalculated, this is a recalculated check digit. You compare the recalculated check digit with the original check digit that was sent to you. If they are the same, then you know that the data is valid, right? You don't verify the data, you ensure that the data is valid. If they are the same, then you can say that it is valid. Perfect. So there you go. That's an example of a check digit where you have some data using which you calculate some sort of digit that involves a mathematical expression or a mathematical equation on the data, which you then transport or save with the data itself, which you can then use to double check whether the data is in the right format and whether the data is, valid on the receiving or on the checking end, right? On the checker's side or the receiver's side, what they have to do is they could simply take the original data, recalculate the check digit, compare it with the original check digit that was sent or saved with the original data. And if they are the same, good job. Nothing is wrong. Okay, so that's the check digit, guys. So we learned about a variety of different validation methods, including all the different checks, range check, length check, so on and so forth, and including now the check digit concept. You do not need to know how check digits work. This simple algorithm is just to show you an example of how it works, although you do have to understand how to explain the process. When I say you don't have to understand how it works, you don't have to understand these expressions per se, right? You do need to understand how to explain the check digit process, but not to an extent of applying it to an equation that you have to memorize and do. If they do give you a question, they will often accompany the question with an equation as well. So you all have to do is just apply the equation with the data, following the given rules, and you'll end up with the result. But frankly, that's less commonplace at the exam. What you'll end up getting is often to explain how a check digit works. Then data verification. Data verification is the other part of data integrity, where the data integrity can be achieved in two different ways, right? It can be achieved using data validation, as well as verification. Now, validation is about checking whether the data is in the right format, whether the data is valid. Data verification is about checking whether the data is accurate or is actually true, whether it's correct, whether the data matches the original. So keep in mind, validation is about formats. It's about the validity of data. We don't know whether the data is actually the true data, right? Such as you entering your date of birth that is in the right format, but may not be your own date of birth when you sign up to Facebook or Instagram. Now, verification ensures that the data matches the original, which ensures accuracy during input or data transfer. Now, like I said, verification can be used during data entry and data transfer. And when it's data entry, you usually use one of two techniques to verify your data, mainly double entry and visual checks. And during data transfer, you use parity checks, block parity, and checksums. Right? So let's take a look at these things. Verification during entry can be first achieved using double entry. Double entry is very easy. Data is entered twice and compared. If the two entries differ, an error is raised. Now, this is very commonplace when you type in a password when you're signing up to a website. Used when typing passwords, where you are asked to type in your password along with a confirm password. If they are the same, then you can ensure that the data is correct. And also, there are some systems when when examiners or when teachers have to input student exam marks into the system, they expect you to enter it twice. Because again, you don't want the exam mark to be incorrect just because of data entry errors. So we enter it twice just so that we know that is absolutely correct, right? Therefore, double entry is an example of verification, ensuring that the data is entered twice and compared, and if the two entries differ, the error is raised. Visual check is a more manual form of verification, which is the next method, where a person manually checks data on screen or in print against the original source. So it's about just checking whether what you're typing is what is correct. So maybe you could check whatever data you're entering into a form against a piece of paper that you have a record of all the records that you're trying to enter into the form, right? So you could double check by ensuring that what you see on screen is exactly what you have on paper. So comparing typed values to a form is another example of visual checks. So verification during data entry can be achieved using a visual check or using double entry. Now we come to verification during transfer. How do we ensure that the data is correct during transmission? First, we have a parity check. A parity check inserts a parity bit, which is a 1 or a 0 at the end of the original data to detect errors in transmitted data. Even parity is one kind of parity check where in this kind of check, the total number of ones in the transmission, in the bits that you're sending, the total number of ones, including the parity bit, must be even. Now, if you send a sequence of ones and zeros, and you count the total number of ones, and if the total number of ones is an even number, that's referred to as even parity. When you ensure that the ones in the number is an even number of ones, right? And if it's an even number of ones in even parity, you know that the data transmission has been correctly sent. If the number of ones is even, that means if you're using even parity and the number of ones are even, the data transmission is true. It's correct. It's not errored out or it's not corrupted during the transmission. Keep in mind, even parity ensures that the total number of ones are even, right? If, for instance, it's odd, it's wrong. You also have the opposite way, right? You could do the opposite check where you check if the total number of ones, including the parity bit, is odd. So here, if the total number of ones is odd, only then is the number, the transmission correct. If it's not an odd number, then the transmission is wrong, right? So two different ways of doing the same thing. And parity check is for single bit errors. Keep in mind, parity checks can only check for single bit errors because if multiple bits change, even becomes odd, odd becomes even again. Odd becomes even becomes odd again. For example, if you have two errors instead of a single error, then the parity may not change. So you might not end up detecting that the data has been corrupt. So it only works for single bit errors, not for multiple or positional errors. I hope that makes sense. Now, let's take a look at a past paper question to understand how parity bits might be tested at the exam. The following binary number is transmitted using even parity, they say. They ask us to add the missing parity bit. So in even parity, what happens? You need to make sure that number of ones is even. So how do you make sure the number of ones is even? Let's count the number of ones in this original data. Keep in mind, this is the original data. And on the left-hand side, they're attaching a parity bit. This is a parity bit, as the label itself suggests. Right? This is the parity bit. Now, what do? We count the number of ones. We have 1, 2, 3, 4 ones. Now, we have 4 ones, right? We have 4 ones. Is 4 an even number or not number? It's an even number, right? So in an even number parity system, what we do is we ensure that the number of ones remain even, and thereby the parity bit is set to be 0. Because if it's 0, then the number of ones have to be an even number. But imagine you make the parity bit a 1. Then the number of ones, including the parity bit, become 1, 2, 3, 4, 5. You end up getting 5 ones, which is not according to even parity there. So keep in mind, if your number system, if your error checking parity system uses even parity, then you have to ensure that the number of ones, including the parity bit, is an even number of ones. So depending on whether it is an even number of ones or odd number of ones, you can make the parity bit a 0 or a 1. Here, it's already an even number of ones, so you make the parity bit 0. Then here, you have another example of a question where you are using odd parity. Here, you need to make sure that the number of ones in the transmission, including the parity bit, is an odd number of ones. Now, if I make this parity bit a 1, what happens? How many ones do we end up getting, including the parity bit? You have 2 ones. Is that odd parity definition like? No. Odd parity's definition says that odd parity ensures that the number of ones is odd. But having 2 ones means it's an even number of ones. That's incorrect. So your parity bit must be 0, right? This ensures that there's only one 1, which means that it's an odd number of ones, right? 1 is an odd number. Okay, so that's an example of parity bits, both even and odd. Now, there's also a concept of parity blocks, right? Parity blocks, where you use parity bits on a grid of data. And let me explain how this works. In the following data transmitted, the following data transmitted, the first column contains the parity bits and the last row contains the parity byte, right? Oops, yeah, seems like there's a small delay, but yeah. The first column contains the parity bits and the last row contains the parity byte. The device transmits the data using even parity. Now what happens, guys, is think about each row. Think about each row separately, first of all. Here they are saying that if you take a look at each row separately, each row acts as a byte where the first bit of that row's byte is the parity bit for that row. Do you understand? So the first column contains the parity bits for each row, you can imagine, right? And this operates based on an even parity system. And then for the columns, also you have a so-called parity bit in the last row. So these last row bits are the parity bits for the column. So at the end, you end up forming a parity byte, which is an entire byte full of parity bits. And they are saying that the device transmits the data using even parity, which ensures that the parity bit should always ensure that the number of ones in that column or row is an even number. They are asking us to circle the error in the data transmitter. So it seems like there's some position where the parity bit may not be 1 when it's supposed to be 1 or 0 when it's supposed to be 0. Meaning the data might have altered itself during transmission, causing the parity bit to tell us that, it was supposed to be even, but it's no longer even. the parity bit was something, but it no longer is representing the same thing because the data may have changed during transmission, right? So in summary, what we're supposed to do is check whether the parity bit is any longer valid for the data, that is either the row or the column, because sometimes if the data has undergone some corruption during transmission, the parity bit may not change. But since there is no longer an odd number or even number of ones, in this case, since there are no longer an even number of ones, the parity bit may indicate that something has gone wrong. And we can use this parity grid system or a parity block system, this is called a parity block, to detect something called positional errors. We can exactly pinpoint and tell us, exactly where the parity bits have gone wrong, and thereby exactly where in this block the error has occurred. So let me try and debug this and help you walk you through how this is solved. Let's take a look at the first row, right? Let's take a look at the first row. How many ones do we have in the first row, guys? 1, 2, 3, 4, 5, 6. Is that an even number? Yes. Are we using even parity? Yes. So therefore, this first row is correct. Then row number 2. 1, 2, 3, 4. That's also an even number of ones, right? So the parity bit being 0 is correct. So row 2 is not a problem. Row 3. 1, 2. That's also not a problem. Row 3 is also no issue because that's an even number of ones there. There's 2 ones, no problem. What about row number 4? Oh, row number 4 only has a single one. Oh, that's an odd number of ones. If this was an odd number of ones, what should the parity bit have been? The parity bit should have been a 1, right? But the idea here is that the parity bit is 0 because it would have previously been an even number of ones before transmission. But during transmission, one of the ones here in any of these positions, maybe one of those ones have become a 0. Do you understand? So therefore, we know for sure that the error has to be in row number 4. What about the column? Let's check our columns now. Again, our columns must also use even parity. So let's check the first column. We have 1, 2, 3 ones. Oh, 3 ones, is it? But that's not supposed to be the case because if it was 3 ones, then the parity bit for that column should be a 1 because 1 plus 1 plus 1 plus 1 is what makes up 4. So the idea is that the data that was sent seems to only have 3 ones, but our parity byte tells us there's technically supposed to be an even number of ones in the data because the parity bit is 0. So what does that indicate? Something would have gone wrong during transmission. Maybe, this 0 would have already been a 1, or maybe one of the ones that are now a 1 may have already been a 0. So this indicates that it's column 1 that has the error because there's an odd number of ones. And then if you take this column and this row and you find the intersection, that's where the error has occurred. So the error can be circled saying that that's where the error is. That 1 is the problem. That 1 should have already, that 1 should have been the one that had changed during transmission. That 1 was corrupted, right? What that means is that should have been a 0, isn't it? That should have been a 0. Is that clear with you guys? Okay. Now, what's the next method of verification during transfer? The next method is to use a checksum. So we already discussed about block parity and also normal parity, but now we're discussing about checksum. A checksum is quite similar to a check digit, but it doesn't ensure validation, it ensures verification, where you have a calculated value that represents the contents of a block or data used to verify data integrity during transmission or storage, right? It's more reliable than parity because it detects many error types, not only single bit errors. And checksums are commonplace in networking and large file downloads. In checksums, what you do is the sender first performs a mathematical operation on a block of data. And then the result, just like in check digits, is sent along with the data. The receiver performs the same operation on the receiving end, and the receiver's checksum is calculated against the sender's checksum. If they are the same, the data is valid. Otherwise, the data has to have been altered or corrupted in some form or shape. Let's take a look at an example, guys. A simple algorithm for checksums could include these four data items: 24, 87, 65, 12, and 41. Let's say that we are using a checksum algorithm where we do step 1, add all the numbers. Let's add all the numbers, shall we? 24 plus 87 plus 65 plus 12 plus 41. You end up getting 229. You attach that to the end of your message, 229. Some checksum algorithms involve modulus operations as well, but we're keeping it simple. You add the numbers and you attach the sum to the end. You can think of this as what? This is the checksum. This is the sum of all the numbers that is used to check whether all the numbers are correct. That's why it's called a checksum. On the receiving end, you take that 229. The receiver will now take that 229 along with the original data, recalculate the sum, which is supposed to give you 229 again. And if this 229 matches the original 229 that was sent with the data, if they are equal, that means the data is correct. Right? That is the data that was originally intended to be sent. Right? Of course, this still means that there is a chance that different data items result in the same checksum, but the chances of that happening in checksum is very low. And usually checksums have more complex algorithms to ensure that the chances of checksum collision, so different data items resulting in the same checksum, is low, right? There are some algorithms that use complex mathematical operations to ensure that the chance of checksum repetition is as low as possible or low as it can be. But here is an example of a very simple checksum process where you just add the numbers together and the answer is going to be the checksum. And on the receiving end, we can ensure that the checksum is correct by recalculating the checksum and comparing it with the sent checksum. If they're the same, all good. That, ladies and gentlemen, completes security, privacy, and data integrity part 2. And if you have any questions, do let me know. And good luck for your exams.